All right. Chapter 2, Part 2. Previously, in Concepts, we talked about Newton's first law. An object in motion tends to stay in motion, and an object at rest tends to stay at rest unless acted upon by a net external force. Or, another shorter way of saying this, an object only accelerates when acted upon by a net external force. A net external force, we mean when the forces are unbalanced. So, in talking about this, we drew these free body diagrams, right? Or force diagrams, where we were able to put all of our forces on, always including gravity, probably a normal force, maybe some sort of tension. If we've got a rope involved, maybe there's friction. And so we were able to look at this and say, aha, well, it's not flying off into space or sinking into the ground, so the normal force and gravity are probably balanced because there is no acceleration in the vertical direction. And then we can look in the horizontal direction and be like, I see. What I see is that the tension is greater than the friction force as I've drawn it. So the net force in the horizontal direction, once I've taken that into account, is to the right. And that's all well and good, but there's a distinct lack of numbers here, and a lack of kind of specificity. So let's see if we can dig a little deeper. Now, we've suggested this relationship between force and acceleration. This is what we were doing, talking all about these motion diagrams, and we were saying that when you have a net force, you get an acceleration. That an acceleration is the result of a net force. So we're saying that acceleration is proportional to, that's what this little fishy thing is, net force. So if I apply a bigger force, I get a bigger acceleration. Do keep in mind, and I'm not going to be able to say this enough because no matter how many times I say it, it's probably still not going to click. A force causes an acceleration. I can push with a certain force, and the object could be moving quickly, it could be moving slowly, it could be moving forward, it could be moving backwards. It doesn't matter. The velocity of the object is not relevant. If I push it, it will accelerate, assuming there's not friction or air resistance or stuff like that. Now, we know more than this. We know more than the more I push something, the more it accelerates. We also know that heavier, by this I mean more massive things, are harder to move. So this gives us another relationship. It says that A, again, is proportional to 1 over m. So if I make m bigger, I make A smaller. You can think of this. If you try to push a balloon, the balloon will accelerate. If you try to push a bear, don't try to push a bear. If you try to push a bear, the bear is not likely to accelerate. Part of this is because, there's more complicated stuff. But mostly it's because the more massive an object is, even in the absence of friction, the absence of air resistance, it is harder to push a heavier object than a lighter object. And by heavier, this is where we're going to get into trouble. The idea of weight is a complicated thing, but we really are talking about mass. Mass. And we will come back to this in a second. If we put these together, we see that if the acceleration is proportional to the net force, so it gets bigger when the net force gets bigger, it's inversely proportional to the mass, so it gets smaller if the mass gets bigger, we see a relationship like this holds. And it turns out it's not even proportional to, it is this. The acceleration as a vector, so the direction of it and everything, is equal to the force divided by the mass. Or, as you may be slightly more familiar with, F net equals ma. A beautiful statement of Newton's second law. So let's take a moment and just kind of bask in this. What we're looking at here, if I hold the force constant, so if the force is the same, the smaller the mass, the bigger the acceleration. If I make m small, I got to make a bigger so that it's still equal to f. If I keep the mass the same, a bigger force means a bigger acceleration. If I keep the acceleration the same, a bigger mass means I need a bigger force. So these are all the relationships we've been talking about here in the last 3.5 minutes or so, and things that you should have probably encountered at some point in your life. We'll explore a few of them in class, but I'm trusting that you have some first-hand experience pushing or pulling things. If not, please come see me. Now, some terminology to be a little more specific. When we talk about mass, you've probably got in the textbook definition that mass is the amount of matter in something, and that if you don't have mass, you don't matter. Or you don't matter if you don't have mass. You don't have anyway, there's a pun in there, but I'm not really fishing it out right now. It is also a measure of how difficult it is to accelerate an object. And this is the kind of mass that we are talking about right now. Sometimes this will be specifically referred to as inertial mass, because it's coming from this idea of inertia, that an object in motion tends to stay in motion, an object in rest tends to stay at rest. So this mass is the mass that says, how hard is it to accelerate? How much force do I have to apply to accelerate it? This second mass, the one the amount of matter in something, is sometimes referred to as the gravitational mass. It turns out these two masses, inertial and gravitational, are one and the same mass. It's one of those cute little things. Didn't have to be that way. You know, charge and mass are different things, and yet obey similar mathematical relationships. And yet, we find that gravitational mass, the thing that measures how strongly gravity cares about something, and inertial mass, that measures how hard it is to move something, are one and the same quantity. Sometimes the universe is nice to us. Anyway, coming back to Newton's second law for a moment, we want to think a little bit about what this looks like in a unit perspective. So, we said F net equals ma. We know mass is being measured in kilograms. We know acceleration is being measured in meters per second squared. So what is net force measured in? Well, if I follow this along, it should be kilograms times meters per second squared. That's miserable. Having to say kilogram meters per second squared is just exhausting. It's vexing. No one wants to do this. So it turns out we replace this with a different unit. We are going to use as the unit of force the Newton. We've already seen examples of this, but I wanted to make sure it was clearly said at least once. And a Newton is a kilogram meter per second squared. We're just giving it a different name to save us a little couple of pen strokes. Now, how do we use this information? Let's say I have a situation like this. I have an object, my little dot. It is being pulled to the right. There is some friction from the ground. There's a normal force, and there is gravity. So, what is the net force? This turns out not to be the question we want to ask. We need to ask both horizontally and vertically. We can only really handle one direction at a time right now. I could have finished spelling vertically, I guess. So let's start with vertically, because that's going to be nice. If I have an object just hanging out on a surface being pulled along, I can look at that and say, in the vertical direction, it is not accelerating. If it is not accelerating, that means F net is equal to 0. And this is true by Newton's second law, which I'm going to tend to abbreviate N2L, because I like to abbreviate things. I can also look at this and say, the net force in the vertical direction is the normal force minus gravity. Because in general, it is going to be all of the forces up minus all of the forces down. This is how we take the vector sum of two numbers. This is one of the things that makes vectors different than scalars, just regular old boring numbers. Regular old boring numbers, you just add them all up. This force is maybe like 10 newtons, the normal force. The gravity, the weight, also 10 newtons. But because they're in opposite directions, I need to worry about that. I need to take the difference of these. I need to take the stuff up minus the stuff down to get the net force. So whenever we're doing these Newton's second law problems, we're going to have one time where we worry about it in terms of MA. That's the whole Newton's second law stuff. And one time where we worry about it in terms of adding up the forces from our free body diagram. So let's take a look at this horizontally. Looking at my free body diagram, I can see, or my force diagram, F net is F pull minus the force of friction. I decided, by the way, that the positive directions for X and Y were as such. That's my choice. I get to do that. You can make a different choice if you want. Oh, good God, everything is ruined. Everything is... Hello? Thank you. You can make a different choice if you want. But it is whatever you like. Now, let's say for a second that this force that I'm pulling with is, I don't know what is going on there. All right, there we go. Is, let's say, 10 newtons. And this force of friction is, let's say, 2 newtons. Then the net force is going to be 10 newtons minus 2 newtons, or 8 newtons. Not quite a fig newton, but what are you going to do? From this, I might say something. Maybe the problem told me that the mass of the object was, very conveniently, 8 kilograms. So I might say, well, that's exciting. I could say then that the net force, by Newton's second law, is the mass times the acceleration. So the acceleration of this object is the net force over the mass is 8 newtons divided by 8 kilograms. Should be obvious now how I picked my numbers, is 1 meter per second squared. So remember, a newton is a kilogram meter per second squared. So if I divide by a kilogram, kilogram on the top, kilogram on the bottom, kilogram over kilogram is 1. This is in general how these problems will play out. Now let us look at one specific example of this in terms of gravity. We've noticed that all objects in free fall accelerate at 9.8 meters per second squared. So if they're in free fall, this is my force diagram. All I've got is the gravity acting on it, which means F net is just my weight. Sometimes this will be called the weight. Your book is going to avoid doing this, and I'll say why in a minute. Well, I have no recollection of what the last thing I said was, but I'm going to hope it was something to the effect of that the net force on this thing is just gravity. That gravity is sometimes called weight, and your book avoids it, and we'll talk about why in a second. So, we notice that all these things are falling at the same rate, this 9.8 meters per second squared. So we're doing Newton's second law, which again, whenever I say F net is equal to ma, that's Newton's second law. The only thing this is equal to is Fg, the force of gravity on this object. So, since A was G, our 9.8 meters per second squared, the weight, the force of gravity on any old object, is always going to be mg, with the caveat that this is near the surface of Earth. If you go up to the top of Everest, things change slightly. If you go into space, or if you're near another gravitational body, things change slightly. But this is a good starting point. Now, let's put this all together and do one more thing. What does a problem look like? So here is a problem. A small package of mass 5 kilograms is pulled along a dirt road by a force of 10 newtons. The acceleration of the package is 1 meter per second squared. What is the force of friction on the box? Now, your book suggests a kind of strategy for these things. It basically says, these are the steps you want to follow whenever you're doing a problem. There are these major things: sketch and translate, simplify and diagram, represent mathematically, solve and evaluate. So let's start sketch and translate. We're going to sketch the process, choose an object, choose a coordinate system, and label information. So this is just kind of things you want to get in the habit of being able to just do. So I've got a small package, has a bow on it, maybe. It's wrapped very nicely. Being pulled along a dirt road. I guess it's a small package, probably shouldn't be bigger than a person. I'm going to pull it by a rope. It's being pulled along a dirt road by a force of 10 newtons. All right, that seems nice enough. What else did I have to do? To choose the object and choose a coordinate system. All right. Package, I choose U. So the package is my object. Everything else, namely in this case the rope and the ground and Earth itself, are my system, or outside of my system, rather, my environment. I'm also going to put a coordinate system in play. Since the package is being pulled, I'm going to say that the direction it's being pulled in is my positive direction. And then, because I don't want to confuse myself, I'm going to make up positive also. What else did I have to do here? Label information. All right. Well, let's see. I've got the mass of this box is 5 kilograms. I've got the tension in the rope is 10 newtons. I've got the acceleration of the box is 1 meter per second squared. I guess we should probably assume, we're assuming that the acceleration of the package, it's accelerating in the direction it's being pulled, and it's not like being pulled to a stop or something. This is all kind of messy, so I'm going to make a nice little table over here. 5 kilograms, the tension is 10 newtons, the acceleration, 1 meter per second squared. Nice. Done, 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 done. Simplify and diagram. Make simplifying assumptions. Already made one of those. We're pulling boxes accelerating in the direction it's being pulled. Make diagrams. All right. So, I don't know if we got anything else we need to assume here. I'm going to assume that it starts from rest. Okay. I'm going to assume I can neglect air resistance. Sure. Didn't tell me anything about air resistance. I'm going to assume it's on Earth. That seems like a fair bet. Although not relevant, I suppose, terribly. Let's see. So, I'm going to make 2 diagrams, a motion diagram and a force diagram. So those are all the diagrams we know how to make right now. So let's see. Motion diagram. It's going to start from rest, and then it's going to have a little velocity, and a bigger velocity, and a bigger still velocity, because those are lazy arrows. It is accelerating, so my delta V is that away. And then my force diagram, or free body diagram, just to make sure I continue my habit of saying 2 confusing things for the same thing. I got my dot from my package. I've got, because the package has mass, Fg on the package by Earth. I've got a normal force on the package. All these things are going to be on the package by the ground. And I've got tension, so thick you could cut with a knife, on the package by the rope. Nice. So I'm going to check quickly. This says that my motion diagram indicates acceleration, so my force diagram should be unbalanced. Specifically, it should be unbalanced in the horizontal direction, which it is. Now I'm going to look and see if I've forgotten anything. Ha! Force of friction. All right. Gonna get some friction in here, I guess. And then leave myself room to actually label it properly. On package by, that's how you spell package. Also ground. Friction, remember, along the surface. Normal force perpendicular to the surface. Both due to interaction with the surface. That seems nice. All right, what's next? Boop, boop, boop. Represent mathematically. All right, so represent mathematically means we're now busting out this Newton's second law business. Since this thing is accelerating in the horizontal direction is what I'm interested in. So I'm going to look at this thing horizontally, and I'm going to say F net is equal to the tension minus the friction force. I'm going to drop all of the extra labels because, quite frankly, it's getting cluttered. Now, what else do I know here? I know, by Newton's second law, F net is equal to ma. And so that is still equal to the tension minus the friction force. And now I want, oops, hold on, before I do that, let's check. Represent mathematically. Boom. This is all I've got. This is my representation of the system. It's got all the information I can have squared away. Next order of business is to solve it and then evaluate it. I am trying to solve this thing for friction. So that means I need to get friction alone. So I'm going to add FF to both sides, because I can do that while maintaining equality, as long as I perform an operation on both sides of an equality. And then I'm going to subtract MA from both sides. Again, maintaining equality. And I have now solved this for FF. It is FF equals stuff that I know. A reminder, we said the tension force was 10 newtons. We said the mass was 5 kilograms. We said the acceleration was 1 meter per second squared. So this is equal to 10 newtons minus 5 kilograms times 1 meter per second squared, or the friction force is equal to 5 newtons, right? Because this is 5 newtons, and 10 newtons minus 5 newtons is 5 newtons. So that is one example of a problem. Basic idea, Newton's second law. F net equals ma. We need to be able to talk about the net force and pull it off of a free body diagram, a force diagram. We need to make sure it's consistent with our description of the motion so we can tell if things are accelerating or not. So there's a lot of stuff, but hopefully the examples help you piece things together.